Okay, so maybe we should slowly start. It's about 2 minutes after, so it's a great pleasure to welcome a friend for many years, Fraydoun Rezakhanlou from Department of Mathematics at Berkeley. So please, Fraydoun, begin.
Thank you, Sundar, for the introduction, and thanks for inviting me to give this talk. It's always an honor to present some of the recent work that I've done, and I think some of you may appreciate some of these works because it turns out to be some kind of central limit theorem for Markov processes. So first, I want to give you a motivation why I'm studying this problem, and this is very much related to some of the models we are interested in statistical mechanics. And after that, I'm going to talk about rather classical work of Groeneboom about Berger's equation, or good old Berger's equation. Then I mentioned a conjecture of Menon and Srinivasan that got me into this work that I'm presenting today for many years. And then I explained that how this conjecture, when you work it out and apply it to Groeneboom's formula and try to use this conjecture to prove Groeneboom's formula, then you end up doing some central limit theorem for a jump process. And then I explained that how you can go beyond Berger's equation and kind of explain a generalization of Menon and Srinivasan conjecture. So let me start with the motivation. And again, this is a problem that has been bugging me for a long, long time. And that is the stochastic growth models. You have some interface separating different phases. The interface is evolving with time, is random. And as is the case for many of models we are interested in, the interface at x and time t changes with a rate that depends on the position, on the time, and the inclination of the interface at that location. And it turns out that as a first approximation, one way to model such a stochastic growth model would be a Hamilton-Jacobi PV. So here I'm assuming that the interface is represented by a graph of a function u that depends on position in Rd, depends on time, and it takes values in R. So uxt represents the height above x at time t. And based on the description that I gave before, it should satisfy Hamilton-Jacobi equation with ut, ux representing the partial derivatives. And basically, I'm saying that the rate of the change of the height function u can be expressed as a function of position, time, and inclination. So ux represents the inclination of the surface at position xt. And this should be coupled by some initial condition. So the initial condition is represented here by g of x. So here I'm kind of studying a growth model that is in continuum, meaning that when you study a Hamilton-Jacobi equation, all the parameters that are involved in this problem are in continuum. X is in Rd, t is in R, and the height u is in R. Though it's very common to study discrete variants of this model, and this would be more familiar perhaps with many of the audience, and they have worked on various models of the same flavor. So x, t, u, if you've seen some of them are discrete, then you may formulate some very familiar models like excursion process and Hammersley-Aldous Diaconus models. So kind of like took some pictures from internet. On the left, you see simulations of Hammersley-Aldous Diaconus model interface. And on the right, you see the one for the exclusion process. For example, for the exclusion process, the position is discrete, the time is continuum, or you can choose a discrete also. There's a discrete variant of exclusion process. And the height is also discrete, whereas for Hammersley-Aldous Diaconus, x is continuum in continuum, time is in continuum, but the height function is discrete. So these are kind of variants of Hamilton-Jacobi equation. And as you may guess, for models we're interested in, we have a random growth, which means the Hamiltonian function is chosen to be a random function. And in the discrete variant, for example, all the randomness comes from a realization of a Poisson point process. These are like black dots on the left in the figure. Whereas on the right, you also have Poisson-like point process, except that the configuration is discrete in the X variable. So you have a bunch of IID Poisson clocks. Though for in the continuum setting, what you do is that you choose a Hamiltonian function that is random and it has certain structures. For example, the most classical example would be a Hamiltonian function, which is the sum of kinetic energy and potential. And the potential is a function of x and t, and that you assume is random. And it has certain structures that would guarantee some of the properties that we are interested in for stochastic growth model. Okay, so since H is random, that means we are dealing with a solution that is random. So we are interested in random solutions of Hamilton-Jacobi equation in short. Okay, so explain some of the questions we would like to address for this model. Let me write phi t for the flow of this Hamilton-Jacobi equation. In other words, I'm expressing the solution as phi t of the initial condition. G is the initial condition and phi t is the solution at later times. So kind of a natural strategy for studying such models is that you select the initial condition randomly according to some probability measure. Then the profile at later time is random and it has a law, and that law is denoted by mu t, and you can kind of express it as the adjoint of this operator phi t is acting on u0. And then there's often people looked at the following question: can you find a nice tractable or explicit evolution for the dynamics of these measures? So mu is changing with time. You want to know whether you can kind of find a nice description for it. Alternatively, you can look at the derivative of u, that is the slope of the interface, and u itself satisfies a closed PDE. That would be a conservation law. And then you want to know whether you can have a description for the law of this slope. And I'm writing nu t for the law of the slope at time t. And well, I mean, in general, that would be impossible, but perhaps for a more realistic question, you may ask yourself whether I can find a nice family of measures that if initially the law is in this family, at later time you stay in that family. Then in this family, you have a kind of more manageable problem, and you want to know whether you can describe the dynamics as you stay in that family. And as we will see, often that family is parameterized by certain functions, and then you want to have a kind of description for the evolution of that function. So kind of I want to kind of give you a general picture of the type of things that we will be able to prove in certain cases, is that we introduce a family of probability measures that are parameterized by a kernel. F is that kernel. And this family, parameterized by a kernel, this family is invariant under the dynamics of Hamilton-Jacobi equation or the corresponding conservation law, meaning that as you apply the dual operator on a choice in this family, mu f, then at later time, you will have still a measure of the same form, except that the kernel is evolved. So you would like to have a description for the evolution of this kernel. I'm writing psi tf for the evolution of the kernel under the dynamics of Hamilton-Jacobi equation or the conservation laws. And it turns out that in some cases, indeed, we can achieve this. And it turns out that When Hamilton-Jacobi equation, when the Hamilton-Jacobi equation, for example, is in dimension 1, and the Hamiltonian is a convex function in P, like in the classical case when the dependence in P is just quadratic, then we can describe a nice family of probability measures that is invariant under the dynamics. And indeed, we derive the evolution of the kernel. And it turns out that when you derive this evolution, you get something which is a kinetic equation. So in fact, I think 2 weeks, I'm giving a talk in Montreal. So I decided to discuss the multidimensional case, which involves very different mathematics in some sense, and it involves some geometric combinatorics. And it has to do with tessellations and evolution of tessellations, Laguerre tessellations. I decided to discuss that in Montreal. And for this talk, I'm going to just focus on dimension 1. Because it's kind of like rather involve a different type of mathematics, though in dimension 1, you can say more. In fact, in higher dimension, the kind of results that I have so far, I have to assume that H is independent of position and time. Whereas in dimension 1, I can allow the Hamiltonian function depends on X and T. And that, needless to say, would be of interest because many of the stochastic growth model we are interested in, we would like to, we do have a Hamiltonian function that does depend on X and T, like the exclusion process or a Hammersley model. These are a discrete version of this equation with the Hamiltonian function depending on X and T. But in this talk, the focus would be the one-dimensional case. And basically, I'm summarizing in this talk some of the works that has been carried out recently. For example, I discuss a work of myself with my former student, Dave Kaspar. In 2 papers, we established a conjecture of Menon and Srinivasan associated with this problem. And then later, we did a work with my current student, Mehdi Ouaki, and a work that of myself that allows the Hamiltonian function depends on X and T. So these are kind of some of the works that you will see in this talk. But before that, let me discuss some examples. Indeed, there are some examples for which you have very nice description of the evolution of the measures. For example, there are some exactly solvable discrete models that are determinantal, meaning that the finite dimensional marginals of these measures can be expressed of a determinant of some explicit kernel. And then when you evolve these measures according to the dynamics of those exactly solvable model, then the kernel of this determinantal process will evolve with time, and you can derive an explicit formula for the evolution of those kernels. Again, the famous example would be totally asymmetric simple exclusion process. And after several works in this context, now we know we can derive an explicit formula for the evolution of the kernel. And in fact, there is another example when everything is exactly solvable and explicit that I'm going to focus today. And that is when you look at the Berger's equation, for example, and assume that the initial data is white noise, or the integrated version of the Berger's equation, which is a Hamilton-Jacobi PDE, if you assume that initial condition is a two-sided Brownian motion. This, it turns out to be a rather exactly solvable model and has a similar flavor as some of the formulas you've seen before for exclusion processes, for example. And the question is that in principle, if H is independent of X and T, and if you start with a profile, which is a piecewise smooth function with stochastic jumps, then you can derive an explicit formula for the evolution. And in fact, you can also allow the H depends on X and T also, but the evolution would be more complicated. And I will say a lot about that case as well. But as a warm-up, let me mention that some of these works started from this rather classical work of Groeneboom that I will describe. In that case, the Hamiltonian function is the quadratic function. There's only kinetic energy, and the corresponding PD is known as Berger's equation. The motivation originally came from the so-called Berger's turbulence.
There's a question in the chat. Does this property hold in law or pathwise?
Law. This is in law. Yes, that's actually very important. Yes, this is actually only for the law.
Okay, thanks.
Sure. Well, a little bit more than law. We're going to discuss it. In fact, it turns out that you can freeze time and look at the dynamics as you vary x, then you can describe the law. But it turns out for some of these models, you can do it the other way around. You can fix t, you can fix space and vary t. Then you can also describe the law, the evolution of the law. But if you vary both x and t, then it's just too complicated. I don't think there is a simple description for it. Yeah, maybe I should pay attention. Oh, yes. The chat. Oh, okay. Next time I will be more alert. Thanks, Sundar. Okay, so here, oh boy, the picture is pathetic. You know, I just copy pasted from a paper. This is a paper of She Oral Fresh back from 1992. This is Berger's equation starting from white noise. So imagine that initially for Berger's equation, you have white noise. Then immediately for positive time, you get a profile that looks like what I put here, except that the picture is pretty bad. So look at the bottom picture, what you see would be a piecewise linear function. So the slope of the function at time t is exactly 1 over t. So that the slope at t equals 0 is infinite, which is compatible with the fact that initially you have white noise. So all these tilted lines at time t equals 0, they become vertical lines. So the slope is deterministic. So you see that the slope of the profile evolving deterministically, and again, the slope is exactly 1 over t, though the jump is random. And Groeneboom figured out the law of the jump. Though I should mention that Groeneboom there is no PDE in his paper. He was interested in a problem in statistics that can be formulated in the following way. You take the Brownian motion and you add to the Brownian motion a quadratic function, and you maximize the sum, and you want to know what the law of the maximum is. And that by Hope-Lax formula is equivalent to solving Hamilton-Jacobi equation with initial condition, which is Brownian motion. And when you differentiate Hamilton-Jacobi equation, that is equivalent to starting Berger's equation from white noise. So you see that Groeneboom's work can be formulated as a problem involving Berger's equation. So let me spell more about the details of the work of Groeneboom in 1989. So again, the setting is that rho satisfies Berger's equation. The initial condition is white noise. And something very interesting happens. When you fix time and vary x, what you get is a stationary Markov process. Well, after all, initially you have white noise. That guy is very stationary. But it turns out that you will have a Markov property at later time. So immediately you get this nice stationary Markov process. This Markov process, as we discussed before, is piecewise linear. So between jumps, the evolution is deterministic. You have a drift. The drift is very simple. It's constant. The constant is 1 over t. And however, occasionally you make a jump, go from rho minus to rho plus. And needless to say that since this is a Berger's equation, the jump can only be downward. So rho plus must be less than rho minus. That's the entropy condition. So you make that jump, and the rate at which the jump happens has a density. So the kernel is given by f rho minus rho plus t d rho plus. And that kernel, again, Groeneboom had nothing to do with Berger's equation, but this is the translation of his work when you do the following PDE problem. Then it turns out that the solution to the Berger's equation enjoys the following scaling. Rho xt and the rescaled version, lambda rho lambda squared x lambda cubed t. So you see that this scaling would be very familiar to those who work on KPZ universality. So they have the same law, and using that and the fact that you start from wide noise initial data, you can easily see that this kernel enjoys the following scaling property, which means that if you know the kernel at time t equals 1 of the solution to the Berger's equation, then you know it at other times. So that's the scaling. And after a very long calculation, you have to see this paper of Groeneboom is pretty hard to read it, but this is, I would say, almost like 15 pages of many calculations, which to me is hard to explain, but he managed to find such an expression for the kernel. The kernel has the following structure. Again, should not come as a surprise. There's some H-dupe transform going on here. The kernel can be expressed as the ratio of J rho plus rho minus times a kernel that now is kind of like a convolution kernel, meaning that the law of the jump, when you make a jump in the profile of Berger's equation, would not depend only on the size of the jump, but the dependence is in such a way that you can express f as the product of two terms. One of them is J rho plus J rho minus. The other one now depends only on the size of the kernel. So this is the size of the jump. This is very much has to do with Berger's equation. This phenomenon would not happen if you switch from Berger's equation to another Hamilton-Jacobi equation or scalar conservation law. But this additional structure is present here. And in fact, this stationary Markov process has an invariant measure that can be expressed in terms of the function j that appears in this kernel. The invariant measure would be the product of j of rho, j minus rho. Again, this may look very familiar when you study Markov chains and Markov processes and construct an invariant measure. This j of rho is the eigenfunction of the kernel associated with this Markov process. And j minus rho is the eigenfunction when you reverse time. Time here is the position. When instead of going from left to right for the variable of the function rho, you go from right to left. And that has to do with the fact that Brownian motion b of x and Brownian motion b of minus x they have the same law, which means that rho xt and negative rho of negative x and t, they have the same law. And when you kind of work that out, that's how it's reflected in the structure of the invariant measure. So the invariant measure is also explicit. Now the question is who J and K are. Now it turns out that when you take the Laplace transform of J and K, then you can express them in terms of airy functions. I'm using lowercase variables to represent the Laplace transform of the uppercase variable. So if lowercase j is the Laplace transform of uppercase j, then is the reciprocal of airy function. And also the Laplace transform of k can be expressed as the second derivative of the log of airy function. So again, it's kind of hard to explain why all these formulas are true, but some of them should not come as a surprise if you're familiar with, again, KPZ equations, all these scalings And some of these airy functions also show up there. Has to do with really this scaling of, T1/3, this cubic scaling that is true for these functions. So maybe I should pause and give you a chance to ponder about some of these explicit formula if you have any question. If not, then I continue. Okay, so that's Groeneboom's formula. So again, let me summarize where we are now. We have an aim, namely understanding stochastic growth models. And as a warm-up, we started with a simpler problem that the dynamics is not random, but it's Hamilton-Jacobi equation or Berger's equation. But I assume that initial data is random. So we started with a simple problem as a warm-up, and we realized that this work of Groeneboom can be translated as a description of the law of this Markovian solution to Berger's equation. So that's what we know so far. Hey, Milton.
Fraydoun? Yes?
Yes, hi.
Hey, so may I make a question?
Yes, go ahead.
Yeah, so I'm trying to understand if you look at somehow a space as time, you see this Markov process. No? So you fix time and you look at this level line, and if you run this process from left to right, you see a Markov process.
Yes.
But you also have a Markov process in time because it's just an evolution, right?
Yeah, right. That's true.
So is this somehow related to this stuff they do which is also related to KPZ about this interlaced Markov processes?
You see, it has the same flavor, but again, here I'm simplifying KPZ equation by dropping various terms. Nonetheless, some of the features are there.
Yeah.
I generalized this. You see, for KPZ equation, you have to allow the Hamiltonian function to depend on x and t.
Yeah.
Then you expect, and I get to that eventually.
Okay.
And I actually explained that there's things you can do in that setting. So there's a class of examples that I know how to treat it. Unfortunately, this class is not rich enough to include KPZ universality.
Okay.
And I explain why. So there's one additional ingredient that I need to add to the whole story that I haven't figured out in details. Intuitively, it's clear what's going on somewhat, but I haven't figured out. But I'll get to that eventually. So first, I want to, as a warm-up, I want to look at this very simple scenario. But again, remarkably, many of the things you see for KPZ equation are already present here.
Yeah.
Okay, so let me continue. So you know that theory, that explicit formula. Now I want to discuss another interesting development. There is this conjecture of Menon and Srinivasan, and the motivation coming from this conjecture are two works. One of them is formula, this work of Groeneboom, and the other one was this work of Bertoine, which says that in the case of Berger's equation, even if you start from a Levy initial data, not white noise, Levy initial data, then at later time, you're going to have a Levy process. And the Levy measure of that Levy process satisfies Berger's equation. So it's kind of a very interesting phenomenon that happens there. And Menon and Pego somehow gave this kinetic description or interpretation of this work. And motivated by these two works, they formulated the conjecture that I'm about to describe. So the way to think about it is that in this work of Groeneboom, you had a profile which is piecewise linear, and you have random jumps. Now, I want to kind of generalize several features of this work. Generalization number one, I want to replace Berger's equation with arbitrary convex function. So instead of a quadratic function, I want to have an arbitrary convex function. Generalization number two, instead of piecewise linear, I better be more flexible, because in the case of Berkeley's equation, you started with white noise and then you had this piecewise linear, which was invariant. That is not going to be the case with general Hamiltonian. What is the natural generalization? Well, instead of piecewise linear, you say it's piecewise smooth. So when I have a profile which is piecewise smooth, it satisfies the corresponding scalar conservation laws with convex Hamiltonian. And in fact, the way to think about it is that for fixed T, you have a Markov process. This Markov process has a drift and a jump kernel. So when there is no jump, it satisfies some ODE. That's what drift means. And I write B0 rho for the drift. But so as you fix T and increase X, you solve an ODE. Though occasionally you make this Markovian jump. There's a kernel that will tell you how long to wait until a jump occurring. And when the jump occurs, it says that with what probability you select a new state, rho plus, if the value is rho minus. So again, this means that between the jumps, you solve this ODE. If you differentiate the initial profile as a function of X, then the derivative is given by B0 of whatever the value of rho 0 is. Though occasionally you make a jump and the jump is given by this. So this is the initial description of the solution to this PDE, scalar conservation laws. And remarkably, according to this conjecture, this picture persists at later times. You again have a Markov process. It has a drift. The drift initially was both B0, now becomes B rho T. So the drift would depend on time. And the jump kernel, when you make those jumps, also evolves with time. And I want to give you a description for both. It turns out that B is going to satisfy this quadratic ODE. So if you differentiate with respect to time, the drift, then you get the second derivative of H times B squared. Be careful here that this ODE, when you solve it, you may have a blow up. If B initially is positive, then in finite time, you would have a blow up for B. So the drift may blow up. And actually the blow up of drift has to do with the occurrence of jump discontinuity. However, if initially B is decreasing, then you would have no blow up. Then you have a global solution. So the way to think about it is that initially I start with a profile that has some jump discontinuities. And I assume that between jumps you have an ODE, but I assume that these ODEs are all decreasing. In other words, I'm assuming that I have piecewise smooth functions, but between jumps, I have a monotonically decreasing function. And occasionally I make upward jumps. If you make such an assumptions, then you do not create new jump discontinuities. You have all these jump discontinuities. These are shocks. The shocks evolve with time. Sometimes the shocks may emerge and turn to a larger shock. So the number of jump discontinuities may decrease, but if I assume B initially is negative, you never create new discontinuities. And it turns out that I can put this condition later on and I can always solve this kind of problems. That I come back to this restriction later. But the point I try to make is that I make a condition, if I don't want to have a blow up at later time, then I make a condition to guarantee that the jump discontinuities may kind of combine to form stronger shocks, meaning larger jumps, but you never create out of blue a new jump discontinuity. If you make that assumptions, or if you solve this problem before a blow up, then you have this picture at later time that you have a Markovian dynamics, and the kernel itself satisfies a kinetic type equation. A kinetic type equation that, if you're familiar, would look like Boltzmann equation. And in fact, the Boltzmann equation is not the right class of examples to compare with. That would be a Smoluchowski equation. in the sense that Smoluchowski equation is a model when particles have size, and when two particles collide, the sizes combine and you have a larger particle, they coagulate. And that's exactly what's happening here, because when you have two shock discontinuities, when these shock discontinuities collide, you will have a shock discontinuity that is stronger, meaning that if the first shock discontinuity separates rho 1 from rho 2, the second shock discontinuity separates rho 2 from rho 3, and they reach each other, then the combined one would separate rho 1 from rho 3, so on and so forth. And so again, the PDE that you end up with, or rather ODE, infinite dimensional setting, has two parts. One of them is a coagulation like kernel, which is a quadratic function, a quadratic operator. It is an integral PDE, so the kernel F would be integrated and is quadratic. And also there's this linear operator, first order operator, that I didn't bother to write them down because it takes pages to write them. I mean, intuitively, they're not that complicated, but it takes time to get used to the very form of these kernels. But these are explicit kernels that you can write down in terms of Rankine-Hugoniot speed of shock discontinuities and the first derivative of H. So first derivative of H and Rankine-Hugoniot slope would show up, would be featured in these differential equations. Okay, so let's summarize the situation. We're interested in stochastic growth. We assume for simplicity that Hamiltonian function does not depend on x and t. Then there are two works. One of them is this Menon and Srinivasan conjecture, and the other one is Groeneboom formula. And Menon and Srinivasan were inspired by Groeneboom to formulate their conjecture. And in fact, Menon and Srinivasan, when formulated this conjecture, they show that Groeneboom kernel satisfies this kinetic equation. In other words, you have a solution that is scaled with time. The formula, I showed it before. You can always express the kernel at time t in terms of the kernel at time 1. And at time 1 is given by this combination of k and j. And, you know, they put that in the equation. And actually, Menon told me that he spent just 1 month to understand what Groeneboom is doing and how this formula satisfies the kinetic equation. But they managed to show that indeed, this kernel is a solution, an explicit solution for this kinetic equation. So that explicit formula that was discovered by Groeneboom does provide us with an explicit solution to this kinetic equation that is, you know, somehow is scaled in a certain way with time, and it enjoys this KPZ type of scaling. And in 2 papers with Dave Kaspar, we managed to establish Menon and Srinivasan conjecture completely. And therefore, we should be able to derive Groeneboom formula directly because we have a candidate for a solution to kinetic equation. So we should provide a new way of proving this. But even that was not clear. So I'm going to spend some time to show that how we can use Theorem 1, which is the verification of this conjecture, and some central limit theorem to show that, in fact, Groeneboom's formula is true directly. We're kind of providing a new proof to Groeneboom's formula, but it's more than that. I mean, it kind of like very interesting central limit theorem will be featured in the proof of this verification of this formula. So again, the idea is that if you use Theorem 1, then it turns out that Groeneboom is equivalent to proving a central limit theorem for certain Markov process. So far, so good. Maybe again, I pause, wonder if everybody's happy with what I'm saying.
So, Fraydoun.
Yes.
I'm a little bit intrigued about this blow up of the drift.
Right. So this theorem says that if initial, okay, so suppose H is convex. If H is convex, that means by entropy condition, you can only have upward jumps. Okay. Now the question is, what's going on between jumps? If I assume the function is monotonically decreasing between jumps, then what happens is that the only thing that can happen is that the existing shock discontinuities, the one that you start initially, they may merge and combine, but no new discontinuity would be created. However, this theory, this work, would not provide you with a solution if in between the jumps, you can decrease and increase. The reason being that in that case, you may create a new shock. It turns out that the way we treat these problems is that we look at the the location of the shock discontinuities, and we treat them as a particle. So what's happening is that you have a collection of particles. They traveling according to their velocities. The velocity is given by Rankine-Hugoniot condition. Rankine-Hugoniot formula offers a candidate for the velocity. And when two particles meet, a new shock is formed. We know exactly what that shock is. But if you allow both increase and decrease between shocks, what happens is that sometimes new particles are created out of blue. If that happens, I have an idea what the dynamics is, but I haven't worked it out. You know, this is the creation of particle. You see, the kinetic equation must be modified because now new particles are created. But I'm kind of first for now, and this is very essential if you want to do KPZ equation. That I haven't kind of worked out the details yet. But if you ignore that for now, then particles interact in the form of meeting and forming new shock discontinuities, but there is no creation of new particles. So two particles can meet and turn to one particle. You may lose a particle every time there's a collision, but no creation of particles. It turns out that when you work it out, when a new shock discontinuity created, you have to create two particles that they move in opposite directions. It turns out that is the right way to do it. So, I mean, the details I worked out, but I still haven't figured out how to modify the kinetic equation to take into account such a phenomenon.
Okay, thanks.
Right, sure. Okay. So this is the idea, but let me say a little bit about the idea because I know that there are so many grand experts in the audience with this kind of questions, but this actually turns out to be an explicit solvable, central limit theorem business. Let me explain that in detail. Okay, so this is the situation. You see, once you have theorem 1, which verifies Menon and Srinivasan conjecture, what it really means is that we have a solution to Berger's equation for t positive, and for each positive t, you have a Markov process. This Markov process is piecewise linear, and it has a jump kernel, and jump kernel, according to Menon and Srinivasan calculation, is an explicit solution to the kinetic equation. So in other words, if you ignore the fact that at time t equals 0, this is white noise, for any positive time, it's just a Markov process, and it fits in the scenario that is treated by this theorem. So for positive time, everything is explicit. The only thing that you have to do is that if you look at the integrated version of rho, which satisfies this PDE, all you have to show is that as t goes to 0, this converges to Brownian motion. So you have a family of Markov processes parameterized by t, and you want to say these Markov processes at t goes to 0 Actually, it's not a Markov process. U is not a Markov process, but it's the slope is Markov process. So this is kind of integrated version of a Markov process. You want to say this integrated version of Markov process converges to Brownian motion. I mean, the first thing comes in mind is that, well, in the setting of a central limit theorem, you have a family of Markov processes, you integrate it, so there's an integral involved, and the integral will converge to Brownian motion. That looks like invariance principle. So that's all you need to check. So if you assume theorem 1, which is a verification of the conjecture, and if you take into account that explicit calculation we have, in order to verify Groeneboom's theorem, all you have to show is that this function uxt, as t goes to 0, converges to Brownian motion. So remember that U rho has some scaling property. It has to do with the fact that Brownian motion has a scaling property, Berkeley's equation has a scaling property. You combine these scaling properties, it says that the process uxt and the process u lambda squared x lambda cubed t divided by lambda, they have the same law. Now choose lambda t minus 1/3 and declare t 1/3 as epsilon. Then it basically says that the process uxt, when you vary x and fix t, and the process u epsilon minus 2x1 and epsilon, they have the same law. But u is the derivative of rho. So basically, it basically says that if you look at the solution to the Berkeley's equation at time 1, which is a Markov process, is well defined. I'm staying away from white noise business. And I know by theorem 1, all these solutions are meaningful because theorem 1 treats piecewise linear Markov processes. Basically says that this Markov process is of 0 average. And when you scale it in the classical way of central limit theorem, you should have central limit theorem and this should converge to Brownian motion. This is the most classical setting I can think of for central limit theorem. So that's all you have to do. But so let's focus on the solution to the Berkeley's equation at time 1. And don't forget that these are piecewise linear Markov processes, which means that infinitesimal generator has 2 parts. One is H prime, which has to do with the fact that the drift is 1. And the other one is a kernel that is given by this solution to the kinetic equation at time 1. So you have this explicit kernel F, that's the jump kernel. It says that you go from rho minus to rho plus, or with this notation that I'm having here, you go from rho to rho star, and you have a jump. And since this explicit solution we have has this H transform type plus something that depends only on the size of the jump, when you work it out, can be expressed in this way. So there are 2 contributions. One is that you multiply your test function h by j and take the convolution with k, because only depends on the jump size, the k part of the story, minus some kind of normalization. I mean, that shouldn't come as a surprise. This is a very familiar formula when you do H transform. When you do large deviation, H transform and all that, you always encounter this. So you have this explicit operator. And the standard trick in this business is that you want to do central limit theorem for rho, you try to find, solve the corresponding Poisson equation. And let's say the solution to this Poisson equation is denoted by W. And therefore, you should be able to relate the central limit theorem you're interested in, namely, let me go back here. Don't forget about this. The last line, you're doing central limit theorem for rho. So all you have to do is attempt to solve this Poisson equation associated with rho and formulate the corresponding martingale. And this LW that shows up here, that's exactly your rho. You want to attempt to do central limit theorem. And then, the first part of the martingale should rescale to 0. So basically, this central limit theorem is equivalent to a martingale plus a small error, provided you can solve this equation. And remarkably, in the case of Berkeley's equation, this operator rather explicitly can be inverted. So we know how to solve this Poisson problem explicitly in this case. In fact, you can do any central limit theorem you want to do with this. More or less, everything is explicit. though you have to kind of invert certain things. You have to, since K and J are rather semi-explicit, you have to take the Laplace transform to express it in terms of Airy function. Otherwise, it's not clear how to solve this, but modulo those details is explicit. And guess what? The solution actually can be expressed as J prime divided by 2 times J. And let's look at the corresponding quadratic variation. So to kind of solve this problem, I basically almost have a martingale. Then I do central limit theorem for my martingale. So it remains to calculate the variance. And that means you have to now look at the quadratic variation. When you look at the quadratic variation, you have to do now law of large number to figure out what the quadratic variation means, what the variance is. So which means that with respect to the invariant measure, I have to integrate this guy, which is just a Dirichlet form. LW is rho. Everything is explicit. The pi, the invariant measure, is explicit. It's the product of J and the negation of J of minus rho. Then the variance is given by this expression. You integrate by parts. You can solve this kernel. You derive a formula for it, and it turns out it's 1/2. By the way, I didn't mention, in fact, in order to have those explicit formula, don't start from white noise. Start from the rescaled version of white noise. It turns out to have those explicit formula is nicer to start with a Brownian motion for which the variance is 1/2, not 1. I'm just following the convention that Menon and Srinivasan did in their calculation. So everything matches. You calculate the variance and you get exactly 1/2, which is exactly the assumption. So that's the proof. You managed to prove Groeneboom's theorem with the aid of the first theorem. Okay, for the remaining 5 minutes, let me mention how you can go beyond Berger's equation. So far, so good. Okay, now this, after feeling good about exactly solvable situation. So the previous situation was exactly solvable. Now I want to go beyond that. Now I want to allow a Hamiltonian function, which is very general. A Hamiltonian function that depends on x and t and is not Berger's equation. Could be anything. The only assumption that I make is that it's convex in the momentum variable. Now, when I'm going to extend the conjecture of Menon and Srinivasan, and I prove that conjecture. So that's a new result that I would like to share it with you. What is the generalization? The generalization is that initially, I'm going to assume that I have a Markov process with a drift that may depend on x, which means my Markov process is inhomogeneous. It's kind of very important to allow inhomogeneity. These are very important if hopefully in future you want to do KPZ universality. And I assume that initially I have a drift, which depends on x. X, don't forget, x plays the role of time for this Markov process. And its kernel also depends on x. And so between jumps, I'm solving some ODE. And the claim is that this picture persists at later time. Meaning that at later time, you're going to have a Markov process, but now drift is inhomogeneous and you have to change it with time. You have a new drift. And the kernel also depends on x and t. Now, if you remember in the previous case in Menon and Srinivasan conjecture, the drift satisfies some ODE, which was quadratic. Now, in this case, it turns out that if you allow the dependence on x and t, the drift will satisfy a linear PDE. That linear PDE does feature that quadratic thing that showed up previously. You see, if h is in, and this is Poisson bracket, because there's some Hamiltonian going on. After all, this somehow is the method of characteristic in disguise. And that's why the Hamiltonian ODE, which is the underlying ODE behind this PDE should be featured. That's why this Poisson bracket would show up. So you have this linear PDE in B you have to solve. That would be the drift. And then the kernel satisfies also a kinetic equation, but this kinetic equation now has like Boltzmann type term there would be a first order term like this. And of course, this is also first order operator. The operator C involves only the state rho minus and rho plus. These are the states of the jump. You jump from rho minus to rho plus. Whereas here, you have a drift that involves the derivative with respect to x variable, like in Boltzmann equation. This is a kinetic equation. And the velocity that shows up here, so remember, kernel depends on rho minus rho plus x and t. The velocity is given by something which resembles the Rankine-Hugoniot formula. So that's exactly the local speed of the jump discontinuity. Again, Q is going to be a coagulation-like operator, like before, and CF is a first-order operator. The only thing is that here, that the curse of creating shock discontinuity is going to show up again. When you look at this B, the equation satisfies by B, if initially B could be positive and negative, this B can blow up in finite time. But if initially you put a condition on H rho rho and condition on B, some kind of mild condition you can put on these guys to guarantee that no blow up happens with B negative. So there is a similar condition you can put there to guarantee that no new shock discontinuity would be added to the system. If you prevent the creation of particles, then the whole theory goes through. But if the new shock discontinuity is created, which is the case for some of the most problems we are interested in, then we have to mollify this theory by mollifying the kinetic equation. And that's a work in progress. It's a time to stop.
Thanks Fraydoun, for a very nice talk.
Thanks, Sundar.
Could I open the floor for questions? Maybe I can start with a question to warm up a bit. Where do you use convexity of H here?
You see, the convexity, you're using the method of characteristics here. And if you don't assume the convexity, then there will be a contact discontinuities. That is not featured here. You see, that's a very interesting question. Let's see how I can put it. Right. So what happens is that if you can do that. I mean, you can allow H which is not convex. Then what happens is that you can have a situation when two particles meet. If H is convex, when they meet, two particles reduces to one particle and continue. If H is not convex, then you have to produce a collection of particles depending on the nature of non-convexity. In fact, what happens is that you see, when these guys meet, then in the middle of it, you have to put a deterministic piece that is going to grow. So this new feature is not included in this theory. If you put that thing in there, then I don't know what's going on. In other words, this kinetic description would not be enough. Somehow you add this deterministic thing in the middle of your profile that somehow destroyed the Markov property. See, Markov property should have this unpredictability in it. But if you have non-convexity, that unpredictability would be destroyed.
So the second derivative being positive, that's somehow part of all that, I guess.
Yes. Because I'm kind of want to avoid that new phenomenon, which is, I call it contact discontinuity. You create a rarefaction in the middle of nowhere. When two particles meet, there used to be shock discontinuities, but then they switch to a rarefaction wave.
So I have a question about the. So I'm still puzzled a little bit with this blow up of solutions because it looks like if you don't, let's say that you want to get the Brownian, the Groeneboom formula, for example, and you say, okay, let's try to approximate our initial Brownian motion by something, okay, that fits into our setup. It looks like if you don't approximate in the right way, you don't get the result.
That's right. So, okay, I know what you have in mind. It's actually a pretty curious thing. You know, I've been thinking about this question, just what you said, it did occur to me. The question is how you interpret white noise. Are you going to interpret it as a jump that going from minus infinity to plus infinity, or a jump that goes from plus infinity to minus infinity? I think that's more or less the question. You see, if you interpret it at minus infinity going to plus infinity, that means you interpret this as shock all over. So initially you have a big bang. Immediately for positive time, all those big bangs turn to a bunch of stars. For any positive time, turns to a bunch of stars, and it turns out to be all shock discontinuities. So what's happening? You see, actually, I think at some point I had a resolution what's going on. So that interpretation is perfectly fine. Just assume everybody initially is jump discontinuity from minus infinity to plus infinity. What happens is that somehow rarefaction and jump living side by side initially. And the PDE is in such a way that suppress all these rarefaction initially and only jump survives. And it gives you a very precise, very tailored approximation, the dynamics of the white noise. And of course, you can kind of interpret it differently, but the dynamics of Hamilton-Jacobi equation somehow suppress all the rarefactions and only shocks survives. That's the right interpretation. I mean, you know, you see, look at those tilted lines. They become straight lines. But you want to think of this straight line going from minus infinity to plus infinity or plus infinity to minus infinity. Apparently, you should think of it as going from minus infinity to plus infinity so that you have entropy conditions.
Thanks.
Are there further questions for Fraydoun? Okay, so why don't we, sorry.
Right, maybe I advertise for the talk that I'm giving in Montreal. So this is story in higher dimension. If you want to stay tuned, I tell you what happens in higher dimension. This is just one dimensional thing. In higher dimension, there are all these new geometric features when tessellation becomes relevant.
Okay, so you're coming to Montreal?
That's right.
Okay, see you there.
Yeah, see you there, guys.
All right, well, thanks for doing.
Thanks, everybody. It was very nice seeing you all.
Thank you.
Thank you very much.
Sure. Bye now.